Swayam Prabha. Digital India. Educated India.
In this lecture, we'll discuss about introduction to statistical mechanics. Before going into the subject, so let us discuss some day-to-day practices that we do with regard to dealing materials and how we talk about them. For instance, if you want to go to a grocery store and buy some water, you go and tell the shopkeeper, give me a bottle of water. Then the shopkeeper asks whether you want 1 liter water bottle or 2 liter water bottle or 300 ml water bottle. So just that is enough to describe a material of a given volume. In another instance, you might want to inflate your bike tire or car tires. So there you go to a petrol pump and a bunk, and then you say that you want to have a tire pressure of, let's say, 30 psi or 40 psi. That's all you mention. So in these situations, if you see, you're talking about materials, but specifying very little amount of information, so that there is a good understanding of specifying the material, and the communication is nearly complete. In the case of water problem, you just only mention water volume because it is understood that you're talking about temperature conditions of room temperature and atmospheric pressure. So you don't have to specify, I want 1 liter of water at room temperature and 1 atmospheric pressure. So it is understood. Suppose if you were to ask a shopkeeper in a summertime, and the shopkeeper may ask you whether you want cold water or normal water. So what he means by normal water is that he is referring to a room temperature water. When you say cold water, he is probably referring to water which is kept in a refrigerator, which may be at 15 degrees Celsius or 20 degrees Celsius, which is little cooler. So, and then if you go to a gold shop, for instance, and then want to buy some jewelry, so there you talk about how much gram of gold you want to buy, and what is the purity in terms of carats, whether 22 carats or 18 carats or 24 carats. So in all these examples, we are able to provide a very minimal amount of information to specify a system, in this case material. So in our day-to-day life, we are able to manage such things is basically a consequence of thermodynamics. In the sense, if you look at a material from a thermodynamic point of view, and you see that even though the material is made up of atoms and molecules, and these molecules and atoms are always in motion, hitting each other, they occupy certain position, they have certain kinetic energy, but we don't have to specify all this microscopic information in our day-to-day life. This is because it turns out that even though the materials are made up of atoms and molecules, when it comes to some properties, these are all averaged out and you get one unique value for those properties. And then it's just enough to talk about very few variables to specify a system. And we are able to also do this because we pretty much are aware of the material that we have been handling. We know about water, we know how the density varies with the temperature, what is the volumetric properties, all that we know. So the point I'm trying to make is that the main conclusion of thermodynamics is being used in our day-to-day life without really realizing what we do and how we do. Okay, so now let us go a little deeper. And in the context of molecular simulation, we have been telling that we could consider a system from atomistic and molecular perspective, and we can build a model which basically tells what is a mutual interaction between these atoms and molecules, and then we can try to study the system by solving set of dynamical equation. So when we solve set of dynamical equation, what we mean is we basically generate time dependent the positions and velocities of all the molecules. So this is a large amount of set of data. So in practical life, we say we don't have to specify all these microscopic details. But then in the molecular simulations, we actually generate such a large number of data with regard to the system's behavior. But what we want to do with this data is a very important question. Ultimately, we want to convert this data into certain measurable quantities, which is available from experimental measurements or from a theoretical estimates. So there comes the question that how do I relate the large number of microscopic data of time dependent position and velocities, and then convert them into certain properties, average properties, which can be compared to experimental systems. So the link between the microscopic data and macroscopic properties, which are either measured or observed, is actually connected through the framework of statistical mechanics. So you can think of statistical mechanics as a framework, mathematical framework, and it takes the microscopic data as an input and then gives macroscopic properties as a output. So when I say macroscopic output, it could be a pressure, internal energy, heat capacity, or any of the things that you can measure in experiments. So because of the reason, we think of statistical mechanics as a molecular foundation of thermodynamics. Because like I said, in thermodynamics, we don't have to mention all this microscopic data. Whereas in statistical mechanics, we provide all this microscopic information, the molecular interactions, forces, and then using such a large amount of data, we try to predict the behavior of a system. So that's the context in which we want to use statistical mechanics in the molecular dynamics simulation course. So now let us elaborate on this a little bit. So when we say thermodynamic state, we know formally how to specify a system depending upon how many components you have, how many phases you have, and what is the temperature pressure conditions. In the case of buying water situation, we know we are looking for a liquid like water. So we don't have to say that you give me a liquid water. So it's implicitly understood. Similarly, when you fill air in your tire, you know that it is on a gaseous state. You don't have to tell them, please fill gaseous air, right? So these are all understood because we are so familiar with it. But then you can subject all these things to a very nice thermodynamical framework. For this case, we use what is called this Gibbs phase rule, which tells you that if you want to describe or specify a particular system, how many number of intensive variables you have to specify. And this depends on the number of components in the system and the number of phases you're talking about, and then pressure and temperature conditions. So this rule is called F is equal to C minus P plus 2. And you can take an example of a single component system in a single phase. This would be like a pure water in a liquid state. There are only one component in a liquid phase. In this case, the F becomes 2. That means you have to specify temperature and pressure for specifying a single component, single phase system. And similarly, you can look at if I go more than one components, and if I go to more than one phases, how many such intensive variables have to be specified. But Gibbs rule only tells about how many number of intensive variables to be specified. But then if you want to study a system experimentally or otherwise, you always have to worry about how much mass I should take, how much amount of material I should take, so that you have a more controlled way of looking at your system. So along with these two intensive variables, such as temperature and pressure, you also need the number of moles or mass of the system as well, so that we know completely how to specify the system. And now once you have this system specification, and then if you know what is known as equation of state of the system. So what is equation of state? This is nothing but the mathematical relation that relates temperature, pressure, and other variables. So this is also known as volumetric properties. So if you are a chemical engineer, you would know that when we talk about gases, non-ideal gases, or liquids, we often write expression relating pressure with volume and temperature, and for a certain number of molecules, right? So once you have this kind of equation of state, then it becomes easy to calculate all the other properties that are of interest. So for example, if you want to know what is the density for a given temperature and pressure, and the density can be obtained from number of molecules by or number of moles divided by the volume. So here the volume is actually obtained from equation of state once you know what is P and T. So you can see in getting the density, we are making use of equation of state to calculate density. And let's say you want to find out what is the heat capacity at constant volume. So the definition of heat capacity is the amount of heat required to raise the temperature at a constant volume. Okay, so it's dou U by dou T. This is a partial derivative, in which case the volume is kept constant, number of moles kept constant, and you're only changing the temperature, and then you see that's the definition of CV. Now for monatomic ideal gas, U is given as 3 by 2 RT. Okay, so now if you substitute this U in this derivative, you basically take this 3 R by 2, which is a constant, it comes out of the differential, and then you have dou T by dou T, which is 1, and then you can see what is the heat capacity for monoatomic ideal gas. So the point I'm trying to say is that it is possible to describe a system with a very few number of variables based on Gibbs phase rule. Once that is known, then if you have the information of the equation of state, then you can actually calculate all the properties of your interest by looking at their definition. Now, in many cases, even the structural quantities such as the structure factor, transport quantities such as diffusivity, thermal conductivity, viscosity. So these are all properties that are related to these are all state functions, and once you specify what the state of the system are, like temperature, pressure, and number of molecules, then all these property could be connected to the equation of state. So this works perfectly fine as long as you have this information such as the equation of state of the system or the free energy of the system. But then there are only very few number of systems which are ideal, pretty much ideal, for which such information, complete informations are available. There are many other systems in which such information is not available. For example, if you want to study carbon dioxide and you don't have an analytical expression for equation of state of a carbon dioxide. So what you do, you try to change the certain variables in ideal gas system, and then you propose a modified version of equation of state, and then you fit with experimental system, and then you do this empirically so that you get a reasonably working equation of state for carbon dioxide. So that's one way how we handle in chemical engineering, by proposing very large number of equation of state. Once we know that, we know how to calculate free energies and other properties. But the way the computer simulation comes in hand here is by providing a framework by which you can actually calculate this equation of state numerically without resorting to any sort of approximation. So that's where we take a system, we model it using certain kinds of forces and interactions, and then using that we generate large number of microscopic variables. So from there we calculate what is these volumetric properties, structural and transport properties. So that's how the MD simulation should be looked at. So now I'm going to discuss certain terminologies and phrases which are going to be very important in this course because we keep referring to these terms now and then. I just now mentioned that a thermodynamic state of a system is specified by a handful of variables such as number of molecules, pressure and temperature, or you could mention volume, temperature and number of molecules. Okay, there are different combinations by which you can specify a thermodynamic state of a system, and how many number of variables required depends on Gibbs phase rule. Now we know that the system is made up of atoms and molecules, like I said before. Now if you want to look at microscopically about the system, you see that all these n particle here would have coordinates and their momenta. Okay, so q1 here is the position of the first particle, q2 is the position of the second particle, and so on. So this goes up to qn, and similarly p1, p2 are the momenta of the first particle, second particle, and so on. So you can see there is about n number of coordinates and n number of momenta, but each of these n will have 3 components in a Cartesian coordinates. So you'll have 3n degrees of freedom from coordinates and then 3n degrees of freedom for the momenta. So essentially you're talking about a 6n number of variables. These are all independent variables. We call them as degrees of freedom. So when you try to describe a system by specifying the individual particles position and momenta, then we say we are describing the mechanical state of a system. Okay, so we want to distinguish between the same system represented in a thermodynamic state and it is represented in a mechanical state. In thermodynamic state, we look at only a very handful of variables such as NPT, whereas in mechanical state, we provide microscopic information of the entire system's position as well as the momenta. Thereby, you are having 6n number of variables. Now, how do we think about this 6n dimensional space? So this is a little difficult to imagine. What I have shown here as this diagram here is a kind of a deformed space. It is actually drawn in a 2 dimension. It is drawn in a perspective view so that it gives us something like a 3-dimensional look. But actually we are trying to look at this figure as a 6n dimensional phase space, and this 6-dimensional space is called phase space. Okay, we keep referring to this phase space now and then in this course. So in this phase space, if I take any one particular position or any particular point which is shown as this red dot here, and then if you look at what is there in this point, you will see that all these n particles are basically specified in this particular location. So if I just zoom in this, what is there in this particular point, you will see there are n number of particles. All these particles are shown as spheres of same color, so that we think of these particles are indistinguishable. Okay, same size, same color. And then I'm also have shown some little red arrows here. These arrows actually point in different directions, and they are also of different length. The direction tells, so these red arrows basically represent the momenta at that particular point. Shorter the arrow, it means its momentum is less, that means its velocity is less. Whereas when the arrow is long, something like this means this particular particle is actually moving much faster than, let's say, this particle. And the directions are talking about which way they are moving at that particular instant of time. So any point in the phase space is a complete description of the entire system. When I say complete description, I'm talking about 6n variables in mentioning about position and moment of all the particles. So mathematically, we use this gamma as a variable that tells you a particular point in phase space, which is a representation of the mechanical state of the system. So now we have 2 points of view. One is to think about in a macroscopic way, the entire system is made up of certain overall temperature, pressure, and number of molecules. That's one way of looking at it. Now another approach is a microscopic approach, where each and every particle's position and momentum is specified at any given point of time in what is called this phase space, which is a 6n dimensional space. Now in the phase space, you see that in this particular point, the systems, so you think of like at a given time t, the system has this particular configuration. When I say configuration, this is about relative positions of the atoms and particles and the respective momenta. So macroscopically, the system conserves the pressure and temperature and number of particles, but microscopically, if you look at it, the distribution of atoms' position and velocity could be different. So I call this particular instant, I call this as a microstate I. So here we are talking about a system overall conserving n and p and t, but microscopically having a certain distribution of positions and velocities, and we designate them as microstate I. Now let's say in another time interval t dash, t prime, time t prime, the systems have moved from this point to this point. Okay, so if I zoom in what is the nature of the system at this particular time, and then you can see still we conserve the number and pressure and temperature the same like before, but locally, microscopically, the atoms have changed their positions and they also have exchanged momenta. You can see when you compare microstate I and j, you can see that the particles have moved from their original positions and they've also changed their momenta, which you can look at by seeing the arrow of each particle have changed in direction as well as in the length. So you can imagine that macroscopically the system is still behaving at n and p and t, but microscopically the system is continuously evolving in time by changing the relative positions and momenta, going from one microstate to another microstate. Okay, so that is what is shown here with the green arrow, going from time t to t prime. So we imagine that the system as moving through this 6n dimensional phase space in time. Okay, and each point in the phase space consists of all the atoms and molecules positions and momenta. And we also use this term called ensemble, which is a collection of microstates. So now here I have shown only 2 microstates, but then I can pick up many such number of microstates in this entire phase space, and then when I make a collection of those, then we call that as a ensemble of microstates. So the manner in which the system travels through the phase space is called trajectories. So a trajectory is nothing but graphically shown here. let's say you start at a particular point here at time t equals 0, and then the system basically evolves through this red line. And then you could start the same system in another location somewhere here independently, and then you can see the system will evolve through the phase space in a different way. So now a trajectory is nothing but the time sequence of the microstates of the system. This where I goes from so where this time goes from 0, t1, t2, t3 all the way to some large time tm, where this m can be very large. So the trajectory is nothing but this particular line in which the system traverses within the phase space. And the way in which the system evolves in time is governed by certain equations of motion, such as Newton's law of motion, or Lagrangian, or Hamiltonian motions, which we will discuss later at some point of time. Now, if you look at the trajectory for a very long time, so here I have shown only a small snapshot, but then if you look at a trajectory for a very long time, you will see that the system will actually go through all possible microstates. So what I mean by all possible microstate is that macroscopically the system should obey the macroscopic variables such as npt. Okay, so in any microstate, if you look at the system, they should conserve number, pressure, and temperature. Okay, because that's something macroscopically specified. So as long as a microstate conserves these npt, and those are allowed microstates, and there are many such in this phase space, and a trajectory will try to sample all those microstates. So now if you choose a particular point in phase space, something like here, and then if you just look at what is the probability that system will be visiting this particular microstate, so that is given by a probability density function known as rho n's. This n's here is the ensemble description. It could be a npt ensemble, or it could be other ensemble. We'll talk about that later. So the important point to remember here is the system is evolving dynamically through the phase space, and a trajectory is nothing but a time sequence of these microstates. And if you look at any particular point in phase space, and then you ask what is the probability that a system will visit this particular microstate, so that is given by a probability density function rho ensemble. So like I said before, an ensemble would be now a collection of all possible microstates. So essentially the trajectory and ensemble are the same thing, because in trajectory also we were talking about a time sequence of all the microstates, very large collection of microstates, trajectory. An ensemble is also a collection of all possible microstates, but the only difference is in the ensemble the collection may not have any time information. So we are not necessarily arranging the microstates in time sequence, but we can just mix them in a whatever fashion you want. So the time information is lost. You're looking at only some all possible configurations or microstates of the system. So that's the only difference between trajectory and ensemble. So in that sense, ensemble has no information of what is the time sequence of the microstates that is evolving through. A good example for understanding trajectory and ensemble is that let's say you go to a function, and then you record a video of the function, and then you see who came first, who did what, and the entire time sequence can be obtained. Okay, so that's one way of looking at the parties happening. The other way is that, let's say a photographer is taking different pictures without any timestamp, and then end of the day he basically gets all these photographs, and then he mixes them up. So in this case you have a lot of information about how the party went on, who did what, but you don't have an information of what happened first and what happened next. So the time sequence is lost. But essentially both processes, that the video as well as the collection of photos, they both basically give the same information about the party, but the trajectory has a little more information about the sequence of the event that happened in the party, whereas in the collection of photos you don't have such a time information. So you can imagine in this particular problem that we are talking about, the trajectory and ensemble has a very similar notion. So in the trajectory we are talking about microstates evolution in time, whereas in the ensemble we are not talking about time evolution, but we are talking about some collection of all possible microstates, which is known as ensemble. An interesting thing is, in this particular ensemble also the microstates will occur this gamma I will occur with respect to the same probability density function that would determine the trajectory points as well. Okay, so thereby we are talking about the same microstates in two different perspectives. Now we come to the measuring a property during this mechanical state evolution through time. So let's say you have certain property A, and that you want to measure in your MD simulations, so that you can compare this with an experimentally measured quantity. So the experimentally measured quantity is known as A observed, and you want to basically calculate this property in your MD simulations. And this property A depends on the microstate. Okay, so depending upon which microstate the system is at, and the property will be different. So then what we can do, now that we have a trajectory of microstates, right, and then we can do what is called this time averaging. So the experimentally measured property should be equal to the time averaged property in your MD trajectory. And then we also say that this property A depends on the microstates. Okay, that's how it's kind of fluctuating over time. And then mathematically you can write that if you observe the property A over a time from 0 to some t observed, and then you basically do the time integral of this value, and then you divide by the total time. In the limit t goes to very large value, then you get a time average. So that's the way in which we do time averaging in MD simulations. In fact, in MD simulations we take a discrete time steps, and then we integrate the equation of motion. So because of that, instead of having this continuous integral, we can replace into a set of sum of variables. So here tau equal to 1 basically means the first time step at which you calculate this property, and then you are looking at the system at a different time points, discrete time points, and then you sum the property of A in those discrete time points, and then you divide by the total number of such observations. Okay, so then this should be tau. So that should also give you a time average, and that should be equal to the observed quantities in the experiments. So this is how we do time average using trajectory of microstates of a given property A. Now we can also do what is called this ensemble average. This is because this Gibbs proposed that we can actually replace the time average with ensemble average, because both approaches, the trajectories as well as the ensemble, talk about the same system's behavior. So we could very well replace one with the other. And let me again recollect that ensemble is nothing but a random collection of all possible microstates without any time information available. And in this collection of microstates, the microstates are distributed as per the probability density function by which even the trajectory points were distributed. And more importantly, the probability density function rho density of microstate depends on what are the macroscopic parameters that we fix, whether we fix npt or whether we fix nvt or otherwise. So depending upon the variable that we control, the probability density function will be different. Now in all these cases, we also talk about whether the system has reached equilibrium or not. From macroscopic thermodynamic point of view, you understand equilibrium means the system's property does not change with time, okay, and it is stationary. So microscopically, what does it mean? Microscopically, it means that the probability density function of the microstates rho ensemble is basically a time independent quantity. Okay, so you can see that the rho dense by rho t is 0. So it does not mean that the system has ceased to evolve. The system is continuing to evolve through the phase space, but the probability of each microstate getting visited, that probability gets constant. Okay, so rho ensemble becomes independent of time, even though the system is evolving through different microstates. Only the probability density function becomes independent of time. But between the microstates, still the transitions are happening. So this basically serves as a molecular interpretation of what is equilibrium means. So finally, what we could do is the experimentally measured quantity A can be either obtained by a time averages from MD simulations, or it could be also obtained from an ensemble average, which we generally do in a Monte Carlo simulations. And so now that each of this state gamma is occurring by a probability density function rho, so we can also write the ensemble average as sum over all the microstates weighted by their probability of occurrence and the value of variable a in those microstates. So now there is another phrase that we often use in MD simulations called ergodicity. So when we say that the time average and ensemble average could be equated, what we implicitly mean by that is the system basically evolves through the entire phase space to all possible microstates. Okay, and so the trajectory should sample all the phase space in the system. Only then the time average and the ensemble average will be equal. Only when this is equal, we say the system is ergodic. And this is not always true. In some cases, it may be that the microstates gets trapped into a very local space in the phase space and it's not going to come out of it. And then if you use those kind of simulation to calculate time average or ensemble average, and that would be an incorrect estimate. So the point that sometimes the microstates getting trapped in a local region in a phase space is pictorially shown here. You ideally want the system to go through the entire phase space, but sometimes there can be some local region where the trajectory gets trapped and it goes about in a very local place like this. And then if you use trajectory points from these set of if you take microstate from these set of trajectories and if you estimate time averages, and you will see that this is not going to be a correct value which cannot be compared with experimental system. So why this happens is because if you look at how the potential energy varies around this region, it may be that there is a particular low potential energy place where once the system gets stuck is not able to jump to the other possible states. Okay, so because of this high energy barrier existing between different states within the phase space, you might have this kind of a trapping of the system in a local region, and this is known as non-ergodic system. An example of a non-ergodic system would be something like if you're talking about glasses or gels, which ages very, very slowly, and it gets stuck in a particular phase space. So when you do MD simulations, it is very important to assert that we are able to sample the system so that ergodicity principle holds. And the way you can check this is by doing simulation with the different initial conditions. Suppose if you start with the initial condition somewhere here, and then you get trajectory from there, and then estimate the property, and then do it somewhere else, and then keep doing few times here and there, and then you see whether your system's property is independent of your initial state. If so, then you're sure that this is basically an ergodic system. On the other hand, if your property that you measure depends on initial condition, maybe that you have a trapped region, something like this, where your property may be different whether you measure it here or outside this trapped region. So it's very important as a simulator to understand the principles of ergodicity and its implication on the measured properties of the system. Other way of showing this phase space is shown here. It's again a 2D representation of phase space. All this hexagonal cell that you see here represents one microstates, and all the arrow that you see here is the trajectory. Suppose if you follow one particular arrow, you can see that it goes through these kind of microstates, and then through this, and then exits here, and then it might enter some other places. Okay, it just goes about in all possible microstates. And this is a region I was talking about where once trapped in this particular region, the microstates get trapped, and then the system visits only some local region and not in the entire region. So doing a MD simulation average in this particular microstate, in this particular trajectory would be incorrect way of doing it. And there are some other regions of similar kind. You can see here, once trapped, it goes into a cycle and it gets really localized. Okay, so representation of phase space is very difficult. If you look at different books, they use different kind of representation. It's very difficult to imagine in our minds how a 6-dimensional phase space look like. Okay, so that's why we often use this kind of 2-dimensional representation or a 3-dimensional representation. But the important point to remember is that whichever way you represent your phase space, each point in that particular phase space will have all the information of the microstate, including the total number of particles, their positions, and their momenta. So now let's see, is there any relationship between the mechanical state which is a cornerstone of statistical mechanics and the classical thermodynamics. And you would expect intuitively, yes, there should be a connection. Okay, so we can see how it can be done. So before that, we'll first take a look at this rho, which is the probability density function of how the microstates are distributed in the phase space. Since it's a probability density function, you can write them as a ratio of some weight function W divided by some Q ensemble, which is known as a partition function. And if you look at how partition function is defined, it is basically sum over all the microstates by their weighting function. Okay, so what this basically means is the weighting function is how many number of possible states are there for a given microstate divided by the total number of all the possible microstates. So essentially this partition function is nothing but roughly translates to total number of all possible microstates. And this weighting function tells you roughly about number of microstate gamma. Okay, so and with this we are only just trying to rewrite the functional form for the probability density function. And then if you go to the ensemble average definition, which is basically sum over all possible microstates, you calculate the property and weight by the probability density function. So now we can substitute for rho n's from this. So you get sum over all microstates A times the weighting function divided by the partition function, and the partition function is nothing but sum over all possible weighting functions. So now for every given ensemble there is a density distribution. For every density distribution there is a partition function. For every partition function there is a thermodynamic potential. Okay, and this thermodynamic potential is generally written as beta times phi is equal to minus ln q ensemble. So here this ensemble is something that we specify as a macroscopic variable. In this case, this beta here is the inverse of temperature 1 by kBT. And you will see that this potential, thermodynamic potential, it attains minimum at equilibrium. So that we know from thermodynamics. So now I'm going to just substitute for different ensemble and then show you what this potential means. For example, if you specify NVE, so that is basically an isolated system, because the energy is held constant, volume is held constant, and number of molecules also held constant. So this is a particular ensemble. In this particular ensemble, the potential is nothing but minus Ts, where T is temperature and S is entropy. So now with this definition, if you go and substitute here, you see that phi psi Ne is nothing but minus Skb times Skb is equal to minus ln Qne. So this is the relationship between thermodynamics and statistical mechanics. So the entropy is given as ln of Qnv. So like I said, Q is something that is referred to all possible microstates, and when you take ln of that number of microstates, that's what is entropy is all about. So many times students find it difficult to understand what is entropy. So we often say degree of disorder, loss of information, and etc. Or we simply say dq by t. But now here you can see that the statistical mechanics gives you a microscopic interpretation of what entropy is. And you can see the entropy is related to the total number of microstates that are available. And when the system reaches equilibrium, you see this entropy is maximum, but the entropy and the potentials are defined the negative. So entropy getting maximum means this potential goes to minimum. Similarly, if you take NVT as an example, instead of fixing energy, if you fix temperature, so this is known as canonical ensemble. In this case, the potential is given by Helmholtz free energy. Okay, so then if you use for mu NVT, if you use A here, you can show that beta times the Helmholtz free energy is equal to minus ln of Q NVT. So Q NVT here is the partition function for the ensemble NVT. So here is the relationship between Helmholtz free energy and the partition function. Similarly, if you fix N, P and T, so if you specify N, P and T, number of particles, pressure and temperature, the corresponding potential is Gibbs free energy, and the Gibbs free energy is related to the partition function under NPT conditions. So you can see that depending upon the ensemble that we fix, there is a corresponding thermodynamic potential, and that thermodynamic potential could be entropy or Helmholtz free energy or Gibbs free energy. All of them are related to the corresponding partition functions. So this is the link between classical thermodynamics and statistical mechanics. So now, what is the context with which we want to look at MD simulation and statistical mechanics? So our objective typically is calculating this kind of an ensemble average, which could be a time average or an ensemble average. Then you can, in principle, try to find this partition function Q, but this number of partition functions are very many, and it becomes impossible to enumerate all the possible microstates. And even if you have access to enumerate all possible microstates, it turns out that many of them are actually weigh very little, because of the fact that many of these microstates are not very relevant because they don't contribute much to the property A. Okay, so the point is, the partition function Q is a very large number of microstates, but we may not need all these microstates because not all of them are equally contributing to the property of interest. So we might be interested to find only certain important microstates that contributes pretty much for the property. In many cases, it is not even possible to directly evaluate the ensemble partition function. I will show in the later class what is the order of magnitude of such partition functions. So that's why in Monte Carlo simulation, what we do is that we try to sample microstates which are very important, which are most significantly contributing to the property, and not pay attention to other microstates which are weighing very less. Whereas in MD simulations, what we do is that we generate trajectories, time dependent microstates, as per the microcanonical or NVE ensemble when we solve Newton's law of motion, and then we try to do time averages using those trajectories. So for other ensamples, okay, so for as far as NV is concerned, Newton's law of motion will give you energy conserving trajectories, but then if you want to look at other ensamples like constant temperature or constant pressure, we have to change this dynamical equation so that the microstates are sampled as per the respective ensamples. So the role of MD and MC simulation is to sample microstates either dynamically or through some other sampling schemes. So whether you do MD simulation or Monte Carlo simulations, all we need to do is we have to find algorithms, numerical algorithms, such a way that we are able to sample microstates given by the probability density function rho. And this algorithm that we are talking about should ensure that it reaches a stationary distribution function, which basically means reaching an equilibrium state. And then we also have to ensure that the ergodicity holds, in the sense the microstates basically visits all possible points in the phase space. So with that, I would like to summarize that in this particular lecture, we talked about a little bit of different set of phrases and concepts, and these may be very new to many of you, but this basically is very important for MD simulations if you want to understand its full potential. So it's very important that you go through and try to understand what is phase space, what are microstates, what is ensemble means, trajectories, and the meaning of time averages and ensemble averages, and the importance of ergodicity so that the ensemble average and time averages could be equated, and what is the microscopic notion of equilibrium means, and partition functions, how the partition functions are related to the probability density function of microstates, and what is the relationship between the classical thermodynamic potentials and statistical mechanics. So these are some of the things that we discussed in this class.